In this video, we're going to look at Lewis structures for molecules. So we looked at Lewis structures for individual atoms, looking at the number of valence electrons. In molecules, we're looking at the collection of valence electrons, those which are shared and those which are not shared. So the dots you see in the pictures in front of you represent unshared pairs of electrons, and the lines represent a shared pair of electrons. So each dot is one electron, each dash is two. In order to make these Lewis structures, there's a kind of a step-by-step procedure that you need to follow that will help you track where all of these electrons belong in a particular molecule. So the first thing you need to do is find the total number of valence electrons that each particular atom is bringing to the molecule. After we do that, we're going to connect all of our atoms with single bonds, with the least electronegative atom in the center, or whichever one can form the most number of bonds is another way to think about that. You then want to add electron pairs to complete octets. Hydrogen, of course, only needs two, and hydrogen can only form one bond for all of your atoms. And then finally, you want to count all of the electrons in the structure and make sure you have no more electrons than you started with. We're really just rearranging, trying to figure out which ones are shared and which ones are not shared. If you do step 4 and you find that you have the wrong number of electrons, well, it's probably because you have some double or triple bonds. So you need to try double bonds, rearrange your dots, see if you can get your total number of shared and unpaired shares of electrons to equal what you found in step 1. And if double bonds don't work, you can try triple. So let's go ahead and put it to the test. So let's find a Lewis structure for SCl2, or sulfur dichloride. First thing we need to do is find the total number of valence electrons. We have 3 different atoms here. So check your periodic table out. Pause the video, see if you can come up with the number of valence electrons we have to work with here. Okay, so you have 6 valence electrons in a sulfur. You have 7 in a chlorine, and there are 2 chlorines. So that's 14, and 6 gets you up to 20 total electrons. And now what we have to do is figure out where to put the dashes and dots to align the number of electrons. Least electronegative element in the center, that's going to be sulfur. The other way is think about this. Chlorine has 7 valence electrons. It's only got 1 unpaired dot in its valence electrons, or its dot structure for its atom. The unshared pairs of electrons are where it's going to form bonds. So hydrogen and halogens can only form one bond, which means they're always going to be on the end. So we'll form single bonds with sulfur in the middle to the chlorines. Then we want to go around and put dots around each element until we get to 8 valence electrons. Well, chlorine there on the right side is sharing 2 electrons with sulfur. That means it needs 6 unshared pairs to get it to 8. The sulfur is sharing pairs of electrons with each chlorine, so it has 4 shared pairs that it gets to claim, and so it needs 2 unshared pairs to get to 8. And so if we pop the dots around there so that everything has an octet, or 8 valence electrons, then what we want to do is count the total number of electrons in the structure. So if you count all of the dots, that's 8 unshared pairs of electrons, so times 2 gets you 16, 2 for each shared pair, so 4 more gets you to 20. So we do in fact have 20 electrons here, and every element has an octet, so that is your dot structure. Let's look at another one. So C2H4. So take a second to see if you can walk yourself through the steps. Find your total number of valence electrons. Hydrogens can only form single bonds, so they have to be on the end of this structure. Those 2 carbons are going to have to be in the center, bonded to each other. Get dots around everything, and then see if you can figure out how to arrange those 12 electrons so that everything has 8 valence electrons and the hydrogens each have 2. Go ahead and pause the video and give it a try. Okay, so hopefully you took a break there and did that. We have 2 carbons, each with 4 valence electrons. We have 4 hydrogens, each with 1. That gets us to a total of 12. Like I said, the carbons are going to have to go bonded to each other in the center, because you can't have a hydrogen in the center. It can only form 1 bond. So if we put our carbons and hydrogens in a structure like this, Next thing we need to do is get ourselves 8 valence electrons around everything, 2 on all the hydrogens. So the hydrogens are all fine, but each carbon only has 6 valence electrons. So we'll get ourselves 2 unshared pairs of electrons on each carbon. Let's go around and count the total number of valence electrons. And what you find out is with 5 bonds, that's 10. And the 2 unshared pairs gets you to 14, which is too many electrons. If single bonds don't work, you want to try double bonds. Well, where can we put a double bond here? A carbon can only have 1 bond. So the double bond is going to have to go, sorry, a hydrogen can only have 1 bond. So the double bond is going to have to go with the carbon. Now, if you count around each carbon has 4 bonds now, and times 2, that gets you to 8 valence electrons. Each hydrogen has 1 bond, which is 2 valence electrons. And we have 6 total bonds, no unshared pairs, and 6 times 2 is going to get us to 12 electrons. So that would be your Lewis structure for C2H4. All right, so see if you can apply this to carbon monoxide. Again, go ahead and pause the video and run yourself through all the steps. Okay, so hopefully you paused the video. Total number of valence electrons here, we only have carbon and oxygen, so it's 4 from the carbon, 6 from the oxygen, so that's a total of 10. We'll put single bonds between, or a single bond between the carbon and the oxygen. We don't have to worry about a central atom because there's only 2. And then let's get ourselves 8 valence electrons around everything. If we count total number of dots and dashes, you get 2, 4, 6, 8, 10, 12, 14. 14 is way too many. Single bonds don't work, try double bonds. So I'm going to have to get rid of 2 electrons before I can put a double bond in there because I don't want more than 8 valence electrons around each atom. So now we're at 2, 4, 6, 8, 10, 12. 12 electrons is too many electrons still. So if double bonds don't work, you go to triples. Okay, let's take a little side trip here. So this would be the dot structure for carbon monoxide, but let's look at what's going on here. If we look at an off-bar arrangement for carbon, we have this situation. 1s2, 2s2, 2 electrons in the 2p. Here we're going to say they're in the 2x and the 2y, but of course they could be anywhere. They don't necessarily have to be up, they could be down. If we look at the electron arrangement for oxygen, we get this situation. So if you want to think about what's going on with these double bonds, the first bond is going to be right here. That's your top bond there, or it could be the bottom, middle, and doesn't really matter. So we overlap these 2 p orbitals. You have 1 up electron, 1 down electron. They pair, and you get yourself a bond. Here might be our middle bond, and so we have 1 up and 1 down again. That's the 2 py's overlapping for those 2 orbitals. And then in the last one, you might notice the carbon doesn't have any, but oxygen has 2. Because oxygen gets a bonus from this bonding structure in that it gets 8 valence electrons, it's going to go ahead and donate both electrons to that pair. And so that last one, both of those electrons come from oxygen, but they are still being shared between the carbon and the oxygen. We call this thing a coordinate covalent bond. A coordinate covalent bond is when one atom donates both electrons to a shared pair of electrons. Okay, so let's wrap up here with doing a little more practice. So here are 3 structures for you to go ahead and try and draw. Notice the last 2 are ions. You should probably go ahead and take a shot at that and see how that works out. Take your best guess on what those are going to look like. And then we'll draw, I'll get you some answers here just after we take a little break while you pause the video and give it a try. Okay, so let's look at the HCN first. Carbon's going to be your central atom there because it can form the most number of bonds. So that'll be your structure on the HCN with a triple bond between the carbon and the nitrogen. When we go to the CO2, notice you have a 2- charge. That means count your electrons for carbon and oxygen, and then there are 2 more electrons than you would expect to have because you have a 2- charge. So you get 6 for each oxygen, which gets you to 18. 4 for the carbon, that gets you to 22, and then the 2- charge is going to get you to 24 total electrons. Carbon's going to be the central atom there. It's the least electronegative. The oxygens are all going to be bonded to that carbon then. And then what you're going to sort out here is that you need one double bond. It doesn't matter which carbon you put it on, or which carbon oxygen bond you put it on. One double bond, the others are single bonds. And then when we do dot structures for ions, you're going to put it in brackets, put that charge on the outside. Having said that and gone through that one, maybe you want to pause the video one more time and make any alterations to your H3O plus that you may have thought of having gotten that answer for the CO3 2 minus. Okay, so there's the H3O plus, all single bonds with the hydrogens. Oxygens can have that one unshared pair of electrons. Again, it's an ion, so we're going to put it in brackets. We'll put that charge on the outside, and that's Lewis structures.